Hi, this is Dion from FocusChemistry.com. Today we're going to talk about energetics and thermodynamics, and I'm going to explain how to solve a question like this from Hua Chong in 2007. Let's take a look at the question. The question states that there are two reactions. This reaction is a reaction where two different reducing agents, graphite and carbon monoxide, are used to reduce iron 3 oxide. So the first reaction is iron 3 oxide with graphite. Iron 3 oxide gets reduced to iron, and of course graphite gets oxidized to carbon monoxide. Enthalpy change of reaction at standard conditions is positive 493 kilojoules per mole. Reaction 2 is almost the same as reaction 1. The only difference is that the graphite has been replaced by carbon monoxide and the carbon monoxide has been replaced by carbon dioxide. Alright, it's the same redox reaction. Enthalpy change of reaction at standard condition is not known. In fact, we're supposed to find this number. Other information that's given in this question is enthalpy change of formation at standard conditions for CO2 at gaseous state is negative 394 kilojoules per mole. And enthalpy change of formation at standard conditions for CO, it's minus 110 kilojoules per mole. How are we going to solve this question where this is the unknown? Well, all of us know from our schools that we need to form energy cycles or energy level diagrams, and we're going to use Hess's law to solve this. So I'm going to talk a bit about Hess's law. What is the essence of Hess's law and how did Hess's law come about? Well, actually, Hess's law is nothing new. Hess's law came about from some fundamental properties of functions like enthalpy. Now, enthalpy, which is a symbol of H, and we also learned in our syllabus there are other kinds of functions like entropy and Gibbs free energy. Now, all these functions are called state functions. State functions. And state functions, basically when we start from a particular state, for example, a certain reactant called reactant 1, certain reactant 1 undergoes a reaction to form a product 1. Alright, let's say it's a single reactant to form a single product. It can form two products, doesn't really matter. Let's say it's a decomposition reaction. And basically, it undergoes this from this reaction, from reactant to products. And the enthalpy change of this reaction is from R to P. Enthalpy change of reaction from reactants to product. This is the enthalpy change for this particular path. And let's say the reaction is reversible, where the products can go back to the reactant, right, in this manner. You find that the enthalpy change of reaction from the products back to the reactant is denoted by this enthalpy change value. Okay. Now, one thing about state functions like enthalpies, in fact also for entropy and Gibbs free energy, is that this particular process is called a cyclic process. Cyclic process means that it starts from a certain point, like here. It's the starting point. And then it undergoes the first path, the first process, alright, it becomes product. Then it goes back again to its original starting point in the path 2. Right? State functions have this property that for cyclic processes, if you start from one point and you end up at the same particular point in this cycle, then basically the enthalpy change of this entire process, where R1 goes to P1 and P2 and then goes back to R1 again, the enthalpy change must be 0. This is a property from thermodynamics about state functions in a cyclic process. So we take a look at this particular reaction here. For this enthalpy change of the reaction from R1 to P1 and P2 and then goes back to R1 again is equals to 0. Now this particular enthalpy, right, is made up of the enthalpies of these two paths, which is R1 to P1, P2, then P1, P2 back to R1 again. Alright, so this is actually the sum of these two enthalpies, which is enthalpy change of reactant to product plus the enthalpy change of product back to reactant. It must be equal to 0. Right? And if you're going to bring this over to this side, you get reactant to product is equals to minus product back to reactant. This is actually following from our cyclic functions, our cyclic process state functions. The sum of enthalpies is 0. So we bring this second term back to on the right hand side, you get a negative sign over here. Now we do know that the negative of the enthalpy of the product to reactant is nothing but just this is basically nothing but just the enthalpy change of reactant to product, right? Because the negative of enthalpy change of product to reactant is the same as the enthalpy change from the reactant to the product. It's the same magnitude but a different sign. Now you notice that this left-hand side is for path 1. This is for path 2. And this is actually the essence of Hess's law, derived from a very fundamental concept of cyclic processes for state functions, is that this is Hess's law, is that if you were to start from a particular point, which is R1 to P1, P2, this is the ending point, you go through path 1, the total enthalpy change in this path 1 is always equal to the sum of enthalpies of path 2. And this is the essence of Hess's law. So Hess's law is actually derived from this fundamental concept of state functions in cyclic processes. And this is how we apply it. As long as the starting point and ending point is the same, no matter which path you take, the sum of enthalpies of each path will always be the same. So we're going to use this concept to solve this question from Hua Chong. For Hua Chong's question, there are actually two ways of doing it. I'm going to show you both ways of doing it. We're going to find this enthalpy change of reaction in two different methods. One method is using one cycle, and another method is using two different cycles. I'm going to do the easier one first, which is the two cycles, which is easier to see. So we're going to start with this unknown as the principal equation. I'm going to copy this reaction over here. The enthalpy change of this reaction, standard conditions, is an unknown. We're supposed to find this enthalpy change. And we're going to see how we're going to use the information given, which is the enthalpy change of reaction 1, the formation of CO2 and the formation of CO to solve this particular question. You notice that we have the formation of CO2 and CO. CO2 and CO happens to be found in this particular reaction. We've got enthalpy change of these two compounds. And we do know the enthalpy change of iron is 0, right? So we have these two enthalpy change of formation. If we had the enthalpy change of formation of Fe2O3, then this particular reaction's enthalpy change can be found. So one way to do this question is to find the enthalpy change of formation of iron 3 oxide first. And how do we do that? We use the reaction 1's enthalpy to do that. So I'm going to draw the reaction 1 cycle at the bottom. This is reaction 1. The enthalpy change of this reaction at standard conditions is given as positive 493 kilojoules per mole. Right? So we've got one compound here, we've got the other compound here, the rest are all elements. So what I'm going to do is I'm going to link this left-hand side to the right-hand side by an alternative pathway, path 2. So this is called path 1, whose enthalpy is actually given to us. We're going to create another alternative path from the same starting point to the same ending point. So the way to link these two, right, is to use the formation enthalpy. So let's take a look at formation. Formation for Fe2O3 is from its elements at the states they are in standard conditions, right? So you need to have 3 oxygen atoms, that is 1.5 oxygen molecules, and 2 iron atoms, which is from here, solid for iron and gaseous for oxygen at standard conditions. Now the carbon here is already an element, so there's no need to change it. So this thing is the same. So you do realize that for these elements to form the left-hand side, the only change is iron and oxygen from Fe2O3, and this is the enthalpy change of formation of Fe2O3. Standard conditions. Alright, and for carbon to form this element, there's no change, so therefore the enthalpy change of formation is 0. Now these same elements to make the left side is the same elements to make the right hand side. So let's take a look at how this thing forms the right hand side. Now iron at 2Fe, the 2Fe there is no change. So the enthalpy change of formation is 0. But enthalpy change of formation of CO from the elements of CO is actually given in the data. This is to form 3 COs. So it's 3 times of negative 110. So this enthalpy can be found. This is given. We can find the enthalpy change of formation of Fe2O3. Now we're going to use Hess's law to solve this. This is path 1 from the left to the right. The alternative pathway is to come down and to go up, so that the two paths start and end at the same point. Start from the left ends on the right. Now Hess's law says that the enthalpy change for both will be the same. So for path 1, the enthalpy change of reaction is 493. For path 2, it's a sum of these two enthalpies. Now do you notice that the blue color arrow, the definition of formation of Fe2O3 is pointing upwards. Our path is going downwards. So the directions are different. We're going to change the sign of that. It's negative enthalpy change of Fe2O3 because we are reversing the direction. And then for this side, the directions of these two arrows are exactly the same. So we're going to keep the sign, we're going to add them together. Alright, and you find that the enthalpy change of formation of Fe2O3 after calculating, evaluating this, is negative 823 kilojoules per mole. So the enthalpy change of formation of Fe2O3 is found. We can use this enthalpy change of formation to find this enthalpy change now. So now we're going to bring this over here. This is the information that we got. So we're going to link this to the left and the right by the enthalpy change of formation as well, in this manner. So there are 2 iron atoms. There are 3 oxygen molecules, 6 oxygen atoms, which is 3 oxygen molecules, and there are 3 carbons. Right? So these are the elements to make up the left. It's the same elements to make up the right. So what happens here on the left, we're going to link them together now, is that this Fe and some of the oxygen here is going to form Fe2O3. It's going to form 1 mole. We've already found that to form 1 mole of Fe2O3 is negative 823. So that is the formation of Fe2O3. And over here, you're going to form 3 moles of CO. 3 moles of CO, the formation is given to you. It's 3 times of negative 110. That is a formation of 3 moles of CO. So that is the left-hand side. Now the right-hand side over here, iron has no change. So the enthalpy change of formation as iron is 0. We're just going to form 3 moles of CO2. Right? So 3 moles of CO2, 1 mole of CO2 formation is 394. So there are 3 moles of them. So it's 3 times 394. Alright, so we form an energy cycle over here. We're going to use this energy cycle to find this enthalpy change of reaction of this unknown. We realize that the left-hand side for this unknown is the starting point. The right-hand side of this unknown is the ending point. The arrow starts from here, ends from here. So this is called path 1, which is the enthalpy change is the unknown. And the alternative pathway, which is path 2, must start from the same point, goes down and ends up at the same point. So this is path 2. We apply Hess's law. Alright. So path 1's enthalpy and path 2 enthalpy must be the same. So path 1 enthalpy is the unknown. In this manner, this is the unknown. This equals to sum of these 3 enthalpies. Do you notice that these 2 blue color arrows are opposite direction from this red color arrow, the path? And therefore we need to change the sign and add them together, add them up together. In this manner. And then on this side, this blue color arrow, it's the same direction as the red color arrow, so therefore we keep the sign, we add them together. Okay, and then you'll find that the answer is negative 29 kilojoules per mole. And this is the answer for this question. Right, so this technique basically uses 2 cycles to find the enthalpy change of reaction of the unknown. Okay, so there's actually another way of doing this, which is combining both cycles together. Just to use one cycle, we can actually find this value as well. Alright. So I'm going to show a bit about the second cycle, the second way of doing it. Again, we're going to use the unknown equation as the principal equation. I'm going to show you a bit of how you do it. This is the unknown. Okay, and this is the enthalpy change of reaction that we're supposed to find. So how can we combine all these 3 information into one cycles? Now, we can bring this equation into this reaction. How do we do that? We notice that this particular reaction requires Fe2O3 to react with 3 carbons, right? But you notice that on this side, there's Fe2O3, but there's no 3 carbons. So we're going to introduce 3 carbons on the left here, in this manner. If we add 3 carbons on the left, you must also add 3 carbons on the right, so that both sides are balanced. Okay? So what we have now is we've got 3 carbons and 1 Fe2O3, which is what we want over this side, and you will form 2 Fe solid plus 3 CO gas, and this enthalpy change is just the enthalpy change of reaction 1. Now the 3 COs will come down here unchanged, so there's no change here, we can add 3 more COs here. Now if you look at the compounds over here and the compounds over there, what's going to happen is that the Fe has got no change. So we're going to think of a way of how to link the COs and the CO2, right? We've already used this information over here. This is used. We need to use these two information to link these two up together. So what we can do is to change all this into carbon and oxygen, then change that back into CO2 again, right? So we can change this into these elements, 6 carbons and 3 oxygen, 2 Fe. So from here to here, there's no change. But from here to here, what's happening is actually the reverse of formation, right? So we come down, what's happening is that 6CO is becoming this, the elements of 6CO. So we need to change the sign because we're reversing the direction of formation, and there are 6 moles of this. All right. Then after that, last step is basically to combine this to form CO2, and that is the formation of CO2 times 6, and this cycle is closed. So this is how we combine everything together into one cycle, and this question can still be solved. The answer will still be negative 29 kilojoules per mole. All right. So this question can be solved in 2 different ways. That's all I have for you today. Thank you for watching, and for more information, look at my website, www.focuschemistry.com. Thank you.